Hi, we're Team 17, and today we're going to discuss our DfM project, which is making improvements on the standard toolbox. The toolbox that we have chosen for our project is a multi-tiered collapsible container with injection molded compartments within it to hold various types of tools or crafting equipment. As shown in the middle picture, when the toolbox is fully opened, there are 3 levels total, consisting of a base layer and 2 collapsible levels with different size compartments that can be modified to the preference of the user. Overall, our predicted production volume falls at around 168,000 toolboxes per year, which comes from our benchmarking of similar products on Amazon. We have 2 types of customers that this toolbox can be marketed to. The primary customer for this product are mechanics, construction workers, and other professionals that are typically known for needing a mobile toolbox to bring with them to different sites. The secondary customer for this product would be people who enjoy crafting, and this toolbox would be used to store craft supplies such as beads, yarn, knitting needles, and more. While the exterior of the product would largely remain the same, the interior would have separate adjustable compartments that would allow for optimal size depending on the customer's crafting needs.
Alright, this is our 5 diagram for our toolbox. So our toolbox has a task function to manage tools, and there are 2 primal basic functions for our toolbox, which are firstly to transport tools that have the basic function of extend grips and organize tools, and secondly, it also has the primal basic function of to store tools, which have the basic function of open container and closed containers. This toolbox also have 4 different primal basic functions, which are assure dependability, that has the supporting function of to protect tools and resist forces and stabilize containers, and as well as to assure convenience, enhanced product that has a basic function, supporting function of adjust configuration, and last but not least, to please senses.
All right, Skylar here with the product analysis functional component mapping matrix. On the top row, we have the functions that our product will perform, and the left side is the components that serve those functions. You can see that many components serve multiple functions, integrating tight, which indicates tight design, as well as the optional variants parts, the divider A and divider B, only fulfill their organizing tools function. This is because we're planning to have different variants that can organize the tools differently. So having our components serve this specific functional purpose and nothing else allows us to keep our design modular for both variants.
This leads us to the component commonality table. In the functional differentiation table, we can see that there are a large number of similarities between the 2 products, but also some important differences. For the most part, the functionality remains the same. Both products will store, transport, protect, and organize tools, as well as providing a gripping point and having the ability to open and close. The major differences are the product's ability to withstand impact, resist the environment, and the configuration that the product will be built in.
To highlight the differences for the different customers, we have placed models of the components we are changing side by side. On the left, we have the tray with smaller compartments. This is designed for crafting supplies such as beads and needles. On the right, we have the blue collar tray with longer compartments. This is designed for tools like wrenches and screwdrivers.
This slide shows the product family assembly diagram. As shown in the original PFAD, some of the platform components are assembled in the beginning, and then the modular components are added before finishing the assembly with more platform components. In order to enhance delayed differentiation, the process was reorganized so that all platform components were assembled before the modular components.
When it comes to designing for manual assembly, we need to select the parts for redesign. The manually oriented and assembled parts are our targets for redesign, which you can see here are the base, supporting tray, dividers, and flaps. When it comes to before our redesign, we're using a number of principles to improve our components. DFA Principle 6, increasing the part symmetry. We apply this to the 4 different trays in our project so that they are all symmetrical in either direction and can be assembled in any order. DFA Principle 10, adding features for easy insertion, adding grooves for components to auto-align as they line up. And DFA Principle 12, Z-assembly, assembling components in the vertical direction, allowing for gravity to do most of the heavy lifting. Utilizing these design principles, you can see that we're able to shave off a number of seconds in our manual assembly process. Before our redesign, this process took 41.5 seconds, and after the redesign, we're now down to 35 seconds.
The subassembly that we decided to focus on for improving the design for automated assembly consists of the small links, large link, fasteners, and handle. The reason for this decision is because the quad chart showed that there's a lot of improvement opportunities with the small links and big link as they are high functional importance and high cost to assemble, and the fasteners are in the quadrant for considering elimination. As shown here, the original design heavily relies on fasteners to hold the links and handle to the base and trays, though it is difficult to orient the parts properly and the links have to be held down until they can be secured with the screws. The total cost for this subassembly is $71, which we were able to reduce using DFA principles 1, 2, and 11. The design post-DFA modifications is shown here. The screws were eliminated and pins with a riveting process were used instead to attach the links and handles to the base and trays, along with reducing fasteners. This also reduced part count and provided locating features, thus reducing the overall automated assembly cost to around $35.
This is the process selection that are compatible with our first material, which is the aluminum metal. Based on the of all the process, there are two processes that suppresses all of the criteria, which are the sheet metal forming and machining. And finally, we ended with the sheet metal forming for our process selection. Secondly, this is the process selection for our second material, which are the thermoplastics ABS, and there are two processes that suppresses all of the criteria, which are the machining and injection molding, and we finally end with the injection molding for our process selection.
Through the process selection method, it was determined that the most suitable manufacturing method for the base would be sheet metal manufacturing methods. When analyzing the sheet metal component using analytical methods, we received a total cost of part to be approximately $1.91 per part. When submitted for a quote to Hubs, Hubs did not provide a quote. When plugged into DfM Pro, the only recommendation provided was to increase the bend radius. In addition to the DfM Pro recommendation, a few more changes were made when redesigning the part to simplify it and make it more producible. Along with the bend radius increase, pilot holes were added, the upper flanges were eliminated, and the embossed holes were flattened. Reanalyzing this part, we received a new cost per part of $1.67 per part, a 12.5% reduction. This time Hubs did offer a quote, but only for low quantities, leading to a skewed extrapolation. Despite this skewed extrapolation, the fact that Hubs did not initially provide a quote, but did for the redesigned part, proves that we were successful in redesigning the part to make it more producible.
Using the process selection method, it was determined that injection molding would be the optimal manufacturing process for the trays. When analyzing the injection molding with analytical methods, we received a total cost of $3.25 per part before the redesign. DfM Pro had three recommendations: follow the recommended rib parameters, to provide a minimum draft angle, and have uniform wall thickness throughout the tray. When redesigning the tray, we implemented multiple design for injection molding principles. We implemented DFIM 1 by reducing the wall thickness to 3 millimeters. We followed DFIM 2 by making all wall thicknesses 3 millimeters. We added draft angles to meet DFIM 3. We rounded the corners to meet DFIM 4. We redesigned the ribs to meet DFIM 5. Our updated analytical costs dropped to $2.36 per part, which is a 25% reduction.
We recognize that tools are often niche and job specific, and it may be a waste of time and money to purchase a tool and use it once. In order to mitigate this, we are offering our Borrow a Tool service. After purchasing one of our toolboxes and registering it online, a Borrow a Tool account will be created. This account allows users to borrow tools for a week at a time and return when done for a yearly fee. But with the purchase of our toolbox, the first year will be free.
Just some overall critiques of our design. We wanted to add kickstands on the far end bases for balance and support, while also modifying the link geometry to prevent the uppermost trays from obscuring the lowermost trays. For the design for assembling, we set it to automated, and through this, the pro is that it reduced the cost by $40, but the production volume and majority of the component sizes don't justify the automated assembly completely. While the design for machining the base, the pro was the simplified geometry and the reduced cost by 24 cents per part, while the con is that it's not particularly aesthetic and it still requires fasteners to hold the geometry. Where the design for the machining of the dividers, the cost was reduced by 90 cents per part, but we do lose some minor storage volume due to the draft angles.